Welcome to the third video about the discrete random variables. Last time we were looking at Bernoulli distribution. Today we will look at its generalization called binomial distribution. A Bernoulli random variable with parameter p takes two values, one with probability p and 0 with probability q equal to 1 minus p. A binomial distribution has got additional parameter n, which is the number of coin tosses in one draw. Let's call our binomial random variable s. S is a sum of independent Bernoulli random variables, each with parameter p. We say that these Bernoulli random variables are IID, independent, identically distributed. Independent means that the value of any one of them does not in any way depend on the value of any other. Identically distributed means that they all have the same parameter p. Let's generate binomial random variable in R. Last time we generated Bernoulli random variable as a special case of R binom function, where we just look at one coin toss. So n in our case was equal to 1. Let's say that we have 10 observations. Let's call it S, or size of our sample, and our probability is equal to 0.4. If we call R binom function and we put size, n and p as parameters, we're gonna have 10 observations with two possible results, 0 and 1. 1 will occur with probability p 0.4. If we now increase the number of coin tosses to, let's say, 5, we will see that there are more possible results. For instance, 3 means that out of 5 coin tosses, we got 3 times heads or ones and 2 times tails or zeros. The minimum number of heads we can get in 5 coin tosses is 0, and the maximum is 5. So there are 6 possible results. If we repeat this experiment, we see that middle numbers like 2 or 3 occur more frequently than extreme numbers like 5 or 0. To get a better picture of the distribution, let's increase the size to 1000 and let's generate a vector of results. A useful tool to look at the distribution is a histogram. In R, the function calling it is hist, and it takes one argument, which is the vector of observations. There we go. The histogram groups the results of the simulation according to frequency of each outcome. So we see that out of 1000 draws, 350 times we get 2s. We also see that the outcomes in the middle, 1, 2 and 3, are more probable than extreme outcomes like 0 and 5. It makes intuitive sense. If we toss a coin 5 times, we expect some heads and some tails. we consider rather unlikely, just getting zeros or just getting ones. Finally, we see that the distribution is tilted to the left. This also makes sense, because we chose the probability of zeros in each coin toss to be 0.6 and the probability of ones to be 0.4. Therefore, on average, we have more zeros than ones. To see this better, let's change the parameter p to be equal to 0.75, and let's regenerate our sample. We see now that the distribution is more tilted to the right, as it is more probable to get ones rather than zeros. So what is the exact probability of each of the 6 outcomes? We will calculate it in the next episode. I hope you enjoyed that, and we'll see each other soon.